Hello, all, and welcome to Chapter 8, Statistics for Math 100 at Google Community College. I'm going to have to apologize again. I still have a bit of a cough going on. So if I am having to leave the microphone to, cough, I apologize for that. Anyways, this is Chapter 8. We're nearing the end of the lecture series. And let's get to it. We're going to start statistics. In this context is more about reading graphs and how to understand data. That's the point of this section. At a very basic level, numbers are used to convey data, right? And you're not always just going to see stacks of numbers. That's boring. That is usually not as effective as it could be. It's not really what you want to do. So as we start here, circle graphs, we can use various means to signify the numbers and arguably the importance that you want to ascribe from them and get across the message much more easily. That's the idea here, right? Statistics. What is that? Well, it's a branch of mathematics that collects and studies data. Sure. Statisticians are basically in everything you do. You are not going to find an area of employment in the world that some step along the line does not include statisticians or people that essentially take the numbers and figure out what they mean. Statisticians commonly use graphs. These give visual representations that are easy to read. Graphs are, you ever picture yourself in a boardroom meeting in a movie. Oh, the profits are way up and the charts are way this way, right? Graphs are used everywhere. Graphs can be misleading. I don't get into that too much in this chapter, but if you want a funny time, go ahead YouTube bad graphs in news or something like that, and you'll see hilarious misinterpretations. Again, because the point of a graph, the point of statistics, the point of presenting data is you want the data to signify what you want it to signify, right? I guess we can just use these two examples here, right? If these were the same data set, you would really question what's going on here, wouldn't you? Because the blue's the biggest over here, but the blue's not the biggest over here. Blue and purple are at the same level, but blue and purple are very different levels, right? I'm not saying these two are the same, of course, but I'm just giving you an example of what I'm talking about. Circle graphs show relationships in parts of a whole, such as this here. There are 10,000 family pets in Grantsville. All right. So if this was a list, if this was a stack of numbers here, I don't think it does the stack of numbers, do they? No, they don't. If this was just a stack of numbers, it would kind of suck, right? You would have 4,035 dogs, 2,590 cats. Oops. Figure this is probably better than me writing it with that stupid pen. 1098 birds, 2099 fish, 272 other equals 10,000 pets, right? If the data was presented to you as written up there, you would probably realize that dogs were the largest section and other was the smallest section, but you'd probably have a hard time comparing them just purely on numbers, right? Well, how much of the dog population, what percentage of the population is dogs? Do dogs plus cats, is that the majority? How does fish and dogs relate to each other, right? That data presents the same information, that data table, as this pie chart, but the pie chart does a better job of explaining how each part relates to the total and how each part relates to itself. How do I delete you? Yes, there we go. This chart here does I think, a very good job of explaining relationships, not only to each other, but also to the whole. So you could look at this, you can say, well, how many pets are either cats or dogs? Well, I know dogs are here, 4385. I know cats here, 2590. So I can add those two up. The data in chart form and in graph form is the same data. Just for this example, yeah, the chart would have worked better. But for other examples, the graph works better. But the graph is always going to be the graph is. All right, let me restart that. For something as simple as this, the graph does everything the chart does, but better. If you get very large numbers, very precise numbers, maybe you have an argument to be made. But you're not going to find a lot of small count statistics where graph does not do a better job of it. You're really not going to find a lot of stuff that is an example of that. And by small count, I mean you're dealing with 6, 8 things, sort of thing, or less. If you have 4,000 individual measurements that you need to take, a pie chart's not going to do it for you. And we'll get to that. Circle graphs for percent values, of course, because what is a circle graph? A circle graph is out of 100. Percent is out of 100. So there you go. Oh, I have to pause the recording real quick and answer an email. I will be right back. All right, sorry for the interruption, folks. As I was saying, a pie chart by definition, or a circle graph as said here, by definition is out of 100. What else is out of 100? Percentages. So percentages flow very nicely into pie charts here. This graph example, we can see Kelsey's $100 monthly allowance. How much is Kelsey's $100 to spend every month? What is she spending that on? 40% of that goes to clothing, 28% of that goes to entertainment, 10% to church donations, 20% to savings, and 2% to miscellaneous. $100 is not a lot of money to spend each month, and she is tithing very nicely, 10%. Good for her. This information could have been presented, of course, in just data form, and it probably would have been something along the lines of this, right? 28, entertainment, etc., etc., etc. But again, we have the issue wherein if I wrote all these down in a big stack of text in a spreadsheet, you wouldn't quite be easily grasping the relationships between the amounts. This does a good job of explaining that relationship. She does spend a lot of it on clothing. Yeah, she does. She puts more on entertainment than she does on savings. Cool. She gives more to the church than she buys chocolate bars, whatever miscellaneous would be. I don't know, $2 a month. What is that, right? I think this person is kind of older who made this chart to think that $2 a month on miscellaneous would be acceptable. But Kelsey is tithing. We got that going for her. I'm very proud of her. Good for you, Kelsey. Since this is percentages, of course, the answer how much is she spending on entertainment is pretty easy. 28% on entertainment, so $28, right? But the cool part is, if Kelsey suddenly went up to $500 a month, you could easily translate this still using this same basic concept. $28 a month, 28% of her monthly allowance, depending on what it is, gets you your total amount. The point is, this is all out of 100% due to the fact that pie charts, by definition, are out of 100%. Pretty straightforward, right? Pie charts, easy to understand, easy to measure. We're doing good there. That was pie charts, arguably the easiest because always out of 100. Bar graphs and line graphs, we are adding to the confusion a bit, but once you understand how these things work and function, you will find that you just need to stop and look at it, right? Bar graphs, helpful in seeing changes over a period of time. Picture shown here. This is definitely, I would say, you don't usually see 3D on 2D. That's just for looks, of course. But what are we looking at? We can obviously see an increase in the size of the bars. Increase in the size of the bars means an increase in what the bars represent. We can see this is the approximate population of Texas. Cool. This is kind of going over the basics of how to read a graph, right? The title gives you a synopsis of what you're going to find in the graph. The axis titles present to you the units of the axis. So these are years, 1940, 1950, 1960, 1970, etc. This is the year. And over here, the y-axis is approximate population in millions, 5 million, 10 million, 50 million, 20 million. We can see as the years increase, the population increases by the fact that each individual bar also increases. Furthermore, we can drag this information back, and if these weren't labeled 6, 8, 10, 11, 14, 17, we could, in theory, right, these are 3D, so this kind of ruins the idea, but we could draw a line from here to here and figure out what's available. Luckily for us, the kind people at Pearson's put numbers in other bars, adding essentially a third axis, if you will, which is exact information. That's not always going to happen. We can use bar graphs the same way we've used data charts before to answer questions. What years did the population increase by the smallest amount? Well, what year had the smallest jump in the bar graph? That's essentially what it's asking. 60 to 70 look the closest. If these numbers weren't there, okay, I just say this bar graph sucks. I don't know why I did 3D shapes on a 2D background. That's not good. That being said, bar graphs work by looking at the bars, realizing how the size of the bar relates to the size of the data point, and then doing your math as you would any other time. So there is no, as I said before, there is no difference between a bar graph, between a graph and a data sheet within small amounts of data. You can still extract the exact same information, and usually it's easier on a graph. There's your arrow. That's very useful arrow. Thank you. Sometimes we have double bar graphs, again with the 3D. What is going on with this, Pearson? I apologize for the cough. That sounds gross. Double bar graphs, useful in making comparisons. This essentially plots two different data points on the same axis. Down here, we have revenue of Riviera Storage, how much money this particular storage company made per quarter, first, second, third, fourth. Here's the revenue in millions, good for them. And the chart explains yellow is 2015 and blue is 2016. So this is essentially putting together two different data points. What's really useful about this, again, is if this was typed up in a sheet, it would probably look something like 2015, then first quarter, is that 11, second quarter, God, this is a horrible chart, 15, third quarter, I don't know, 28, fourth quarter, 31. Who decided to make this? And then 2016 would be below it. And then it would not be quite as easy. Is that supposed to be 14, maybe? It would not be quite as easy to do these direct comparisons by quarter, right? You want to do an issue wherein, et cetera, et cetera. You run into an issue wherein you can't easily compare quarters per year because you have to jump around the data, the charted data. You have to jump around your spreadsheet in order to find your comparison. If you want to compare, if you want to find the first quarter wherein the 2015 outperformed 2016, that's easy here. That's completely obvious. On this chart, you have to literally go to each one back and forth and drag your eyes around until you find the difference. That's a problem. That's extra time that's wasted, especially when you present this information to people who don't care about the actual numbers. They just want the answer. Presenting this information as a big chart, as a big spreadsheet, and having them find it on their own, they're going to get mad, right? Think of that grumpy office guy from any boardroom meeting in a movie you've ever seen. Just get to the point, damn it, sort of stuff, right? Graphs are very useful. Yeah, exactly. To which quarter did revenue of 2015 exceed revenue of 2016? Bam, third quarter. Easy to answer. Look at that. Yellow is taller than blue. I'm done. I don't need to know the numbers. I just need to know that third quarter 2016 didn't do as well. Then, again, in your office setting, well, why didn't that happen? Well, we made this change. Well, let's not make that change again, right? If this was in spreadsheet form, would not be as useful. Line graphs are essentially the same thing as bar graphs, just they include a perceived rate of change in between steps. Line graphs always follow each dot represents one data point, the exact same way that bar graphs do, right? Each bar represents one data point. Just a line graph connects these with a slope. The slope, by definition, is not accurate. The slope just connects the lines. The month of March to April could have went like this. Could have. But the chart's only going to make that straight connection because of it plots data points exclusively. How many more customers were there in May than in April? Well, here's May, here's April. Look at the line. That's 22, and that's 14. So you're talking 5, 6, 7 more customers. 7,000 more customers, sorry. Hopefully Bank of America doesn't have 7 customers in it. Just the same, I keep beating that dead horse, right? Just the same as a big old table of data points, except it's visually more appealing and it's easy to make these connections. The exact amounts, perhaps, are not as easy, but the fact that April and May had the big jump is probably what you're using the graph to signify. You don't use a graph to signify specific numbers. You use a graph to signify relationships, as I said back in the circle graph pie chart explanation from earlier. Oh, sorry, they said 22 and 4. I don't know how I'm supposed to be able to tell that this is a step of 2 and that's a step of 1. I have no idea. But then again, I'm not Pearson's. I don't know everything. Interpreting comparison line graphs. This is the exact same graph as the double bar graph we showed earlier, right? The blue is 1 year, the green is another year. I could say, okay, these are the years of 2013 did better than 2012. When 2003 did better than 2002. And that simple answer comparison is a lot easier to do in a chart like this than it is to do in, say, a stack of data. I'm not going to draw the stack of data again because that takes forever. And I hope that you're understanding the point I'm trying to make here. Right here, January, February 2003 had more total snowfall in Ohio than 2002 did. 2002 had more snowfall in November, December, and March. 2003 had more snowfall in January, February. Easy to answer just by looking at the chart. They go with which month had the biggest difference. Works as well, right? You could just look at what 2 data points are furthest away from each other and answer the question. Something I'll point out here is that all the examples they're using for line graphs could have just as easily been done with bar graphs. This being a line graph or a bar graph makes no difference in this particular question. What does make the difference, however, is as I said already, the perceived slope. Actually, let's do a different color there. The perceived slope changes. That's the interesting thing. This slope here versus, let's do pink. This slope here. That is the thing that a line graph does a lot better than a bar graph explaining. We had a massive drop off in snowfall between February and March 2003, and we had basically no change in snowfall February to March 2002. That's the benefit here. Because if this was a bar graph, there wouldn't be any difference, right? And as a bar graph, this would be pretty easy to draw, right? Let's do a darker green. There we go. Just draw little bars underneath the dots, and you have yourself a bar graph. Let's do blue over to the side here. There we go. Although actually blue should be on the other side. There, whatever. Right? If those were bar graphs, you could see these same changes. You could see the same amount differences. And that question would be just as well answered with a bar graph. I hope that makes sense. I'm kind of belaboring the point here. But when you get to either more specified classes or more difficult math classes, knowing what charts to use, what types of graphs to use is very important. There's a vast variety of graphs out there, histograms being one, and choosing the best graph to represent your data in the most efficient way possible could be the difference between landing the big job and being passed over for the big job, right? Histograms are unique in that they do not actually plot data, they plot frequency of data. They'll, as it says here, they're used to organize and display results from a table. You have here the test scores for 31 students. 4 of those students score between a 60 and 69. So what we're going to do is we're going to say 60, 69 is our new data point, and there are 4 people that fit in that. I think the term usually box you hear sometimes, or man, I'm forgetting the word top of my head. There's a specific word for what this is called, and it usually actually, funny enough, can relate to coding. This is usually not in coding, but anyways, this particular group of scores is represented here. The individual scores are not what you care about for a histogram. This could have been a score of student 1 got a 60, then student 2, student 3, student 4 all got 69s. That could have been the grading for these scores, meaning the students, 3 of the students got very close to a C, only 1 student did low D really bad. But they're all going to be grouped together because what you care about is the D, C, B, A grading. What did my students do? The majority of my students got a B on this test. That's the point of a histogram. If this was, again, individual grading, and you could say blue is 60s, and this was a bar graph, something like that, right? Red is 70s. You could, if the bar graph looked like this, orange is 80s, bar graph looks up like that, it may not be as easy to tell, well, most of the students got the 80s score from, let's say, the 70s, because the 70s may have a wider variety of scores, but the 80s had more total students in it. Does that make sense? They might get in this a bit. Let's say 84 was the most common score. And a lot of students got an 84. A lot of students landed a B. But there was a big variety. That's a terrible looking 7 right there. There's a big variety of 70s that a few students got. Instead of making that, I guess I could just type it too, but instead of graphing it in the instead of graphing it in the previous styles to say, see every student as its own individual bar or line, clumping them together allows you to answer the question you want to answer. Again, the question probably would be, what grade was most common for the test? A, B, C, or D, not 80, 81, 82, 83, 84. How many students scored an A? Well, 6 of them. Again, that's something that could have been done with most any chart, but histogram does the best job of explaining how many students got an A, because an A is quantified by this box. If I know how many students got a 95 or higher, this histogram does not do a good job of that. But how many students got 90 or higher, this histogram does a really good job. And if the data was all drawn in a table, you're really going to lose. It's really going to suck to figure out what of those was an A and how many students had A's. How many students have a passing grade of 70? Well, again, just look at your histogram boxes. Like, there's a better word for that. I'm sorry, I can't remember off the top of my head. Look at your histogram boxes here and say, okay, these are all 70s, these are all 80s, these are all 90s. I can draw a line over here to figure out exactly how big these boxes are and know my answers. Again, I'm going to stress here, they keep giving you questions that are better answered in other means. A histogram is not useful for telling you how many of something. Histogram is useful for comparisons. If I asked you this question, no one would go over this chart here and draw the lines. You'd go over here, right, to this data spreadsheet. Oh, excuse me. But I hope what I'm saying is coming across to you in that the point of the histogram is to do comparisons. The point of the pie chart is to do comparisons. The point of the bar graph, the line graph, is to do comparisons. If you need exact numbers, don't necessarily use a chart because it's going to involve the extra work of drawing in your head the little lines over, right? If you need exact numbers, use a table. If you need comparisons, use a chart. If you need both, use both. Very common. How to construct a histogram? Well, you start with raw data that is yet to be organized or interpreted. You organize it, and then you graph it accordingly. Here are the average monthly salaries of 24 college students. Some of these kids have good jobs. That's a pretty good job, right? So, in order to turn this data into a histogram, in order to turn this data into a histogram, you first need to define what you want your histogram bins. Bin. That's what they're called in coding. Bins. Yes, go me. You need to figure out what the bin you want to put this data into will be. You put the data into it, reorganize into your histogram, and then you end up having the result that makes sense. So, in this case, it says select data class intervals of equal width for the data. Or boxes would work, I guess. So whatever sticks best with you, right? So select your data class interval. What width do we want to all consider to be the same thing, right? In the previous example, a B was an 80 to an 89. So we want to look at this data and figure out those sort of steps. And then after you figure out how large your bin is, how large your data class is, how large your box is, find out how many pieces go into it. Good examples of this would be maybe like, I don't know what they're going to do, but if I was to get this and you wanted me to bin this data, easy binning would be, say, 0 to 500, 500 to 1,000, 1,000 to 1,500, 1,500 to 2,000. There's 4 bins. You could break it down more into 250 bins if you want. It all depends on, again, what your end goal is going to be and what you want this information to represent. If the smaller bins of 250 better represent whatever point you're trying to make, use the 250s. If the larger 500 bins better represent the points that you make, use the 500s. If you need to go down to 100 bins, which would be 2 to 300, 3 to 400, 4 to 500, bin it that way as well. They're doing 400 bins here, right? They're saying 100 to 400 being our first bin, our first box, our first interval. And then 500 to 900, essentially, 900 to 1,300, 1,300 to 1,700. So our bin size, or interval size, is about 400, 399, but we'll call it 400, right? That's our bin size. Each of these bins is of equal size, so I can make a histogram then. Cool. With that information, I just need to say which of these numbers goes in which bin. Put the number in the corresponding bin, right? 323. Well, that fits between. Yay, look at that. Whee. 323 fits there. Cool. So that individual number is going to go in that individual bin. What does 598 fit? Well, 598 fits in the second bin. Cool. You're going to put all of these numbers into these bins, and then you're not going to care about the numbers once they're actually binned. That's the important part here. You're not going to care about these numbers. You're instead going to care about how many times a number goes in each box. If you look at the numbers I've done here, bin 1 so far has, let's do it this way actually. Bin 1 has 1 box in it. Bin 2 has 1 box in it. Bin 3 has 2 boxes in it. Bin 4 has 1 box in it so far. So my histogram is going to kind of be that already. And then as you bin more numbers, your histogram grows accordingly. See here, I can bin 250 here, bringing this total number up to 2, and my histogram would rise accordingly. And what you do, of course, is you don't do this in steps. You don't build the histogram with each individual inclusion. You instead note how many parts are in each individual bin and each individual class interval. And then you, at the end of the day, you look at this number over here and you make your histogram based on the final total, if that makes sense. This is probably one of those things where you just need to do it a couple times. The truth is, this is a very easy mechanical step. It can take a bit of time, and these things are usually done with computers. Excel or Google Sheets has a histogram feature where you can set bins and just automatically put all your data in, right? But it's important to know what they're actually doing. So yeah, so it says here, make a tally count of how many numbers occur in each interval. There we go. If you did the bin, if you kept going with that process I was doing, it would have got ridiculous with all the arrows, right? You have noticed that this chart here has 9 students in it that make under $500 a month. This chart has 800 students that make between 500 and 900. This chart has 5 students that make between 900 and 1300. And this chart has 2 students that make over 1300. That is your tallies of your bins and the sizes of your bins, thereby making you histogram, telling you the majority of students make less than 500 a month, and the overwhelming majority of students make less than 900 a month. Those are quick takeaways from this chart. Very few students make 1,300 a month. Very few. And the comparison is what's important here, not exactly the strict numbers. This top chart here, this spreadsheet, that's your quick numbers. 2 students make more than 1,300. That's your quick information. The histogram says very few students comparatively make 1,300. This is a better job of representing the dynamic relationship of the data. And this guy up here does a good job of giving you the specific relationship of the data. Cool. That was different ways to represent data. There are plenty of different ways to do it, right? Next time you go in Sheets, just look at all the chart combinations of Excel. Look at all the chart options you have. It gets ridiculous. But please, 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 never do what Pearson's did at the very beginning here. Never do 3D if you don't have to. Those are ugly. I'm very upset at Pearson's for doing this. If I cared more, I'd make new charts, but that involves effort. So don't do 3D if you don't have to. That's just ugly. Well, how am I supposed to know any of those numbers? What do I measure off of, right? That's a 6. Is it off of which corner exactly am I measuring that 6 off of? Horrible charts. Do not do 3D unless it actually serves a purpose. And in some cases it will. In those cases it did not. All right, enough beating up on Pearson's. Let's move on. Mean, median, mode. These are three phrases you're going to hear a lot when you do statistics. It's basically the core of statistics, and they all are very applicable and very useful in basically any situation where you have to interpret data. Mean, median, and mode are sort of the baselines of using math. What are these words? Well, your mean is a set of values. The mean of a set of values is the sum of the values divided by the number of values. Synonymous with average. A mean and an average kind of represent the same thing. And if you know what an average is, you know what a mean is. Mathematically speaking, it is add up the numbers, divide by the number of numbers. You've probably heard that before. If I want to know the average weight of high school heavyweight wrestlers, I take all the individual weights, all these, add them together, 2066, and then divide by the total number of wrestlers, 10, to give myself an average weight for said wrestlers. All these wrestlers, this guy is real big, 250-pounder. Oh boy, it's a big high school wrestler, right? And these two down here are pretty small, 187. Actually, that's not small really, but there's a big difference between these 180s and this 250 and this 223. But on average, they all come down to slightly over 200. Probably because there's only 3 that are massively exceeding 200, and everyone else is kind of right around it. Right? That's a mean. I could write down an equation for you, but it's almost better remembered as a phrase. Add up the numbers, divide by the amount of numbers. That's a mean. And the other thing I'll say about mean is it is something you just need to kind of do. If you have the stuff in a spreadsheet, it'll calculate mean for you. But if you don't want to put the numbers into a spreadsheet, you just need to sit there and add up each individual number, then write down the total of everything you added, and then count how many numbers you have and write down that number. And actually drawing this equation out before you answer it means you did it correctly. A median is what you get when you arrange the numbers from smallest to biggest and find the middle position. That's the median, the center, right? The center of the set of numbers is the median number. Sometimes it's useful, sometimes it's not. I guess I should say at the beginning also, each of these 3 things varies in how useful they are. Sometimes your mean is very important for what your question you're answering. Sometimes your median is very important for the question you're answering. Sometimes your mode is. They all vary in usefulness depending on the question. If I want to know the median of those said heavyweights, I'd have to take this random data set, organize it, literally draw it out and organize it. Don't try to do it in your head. You're going to get lost. And then usually you just kind of cross through the outside ones, work your way in. Bam. Right here, if you have an even number of totals, your median is going to be between the two. If it's odd number, you're going to land on a specific number. The median is between those two. So you probably say 198.5 is your median. And this is a good example of how is that information useful. In this particular question, I don't really know how median is going to be beneficial. I could see mean being beneficial. My wrestling team has an average weight of about 200. I want to get that up. You thin boys, stop packing on the muscle. That I can see being something useful. Median, for this example, not so much. But then again, you're going to run into situations where median is the thing you really care about. Mode is the most often number in a particular set. Again, going back here, what number appears the most? 187 is the only number that appears twice, therefore 187 is your mode. Not all numbers have mode, if every number is different, or if every number has the same amount of numbers in it. If a set has 2 of everything, there is no mode. If that has one of everything, there is no mode. This example, there is a mode, and that mode is 197. Is that particular information useful? I don't know. Maybe if you go into weight classes, you want to know how many wrestlers fit in each weight class, or what is your strongest weight class by amount of wrestlers. That could be useful. Let's say you have a 187 weight class or something like that. These numbers, let's say these numbers are a bit more divergent, and you had to know, well, 187 is my strongest team to put out there. That's a usefulness of mode. You could almost say mode and histogram are related, but they're really not. And yeah, that is statistics. I told you it'd be a short day, right? Hopefully you understand these very basic concepts. Mean, median, mode, you really should make sure you have down. You're not going to find many situations where where you're dealing with numbers and you're not having to deal with at least these three. You're not going to find many. When it comes to charts, histograms, it's important to know the difference between a histogram and a bar graph. Very important to know those differences and to recognize it. You got a histogram if your x-axis usually has sets of numbers in it. A bar graph's going to have a number. Histogram's going to have a set of numbers usually. And that's my other big thing is I'm going to go back to this stupid slide. Do not do this. Do not put random 3D shapes on your graph. It makes it look like a middle schooler did it, and it is bad. Do not do this. If you turn in a homework or a test, I'm just going to give you a 0 on the test if you decide to pull this crap. Do not put random 3D shapes in on your charts. You will be fired from your job for doing this because this is stupid. Look, it has shading. Why does it have shading? Where's the light source coming from? There's so much wrong with this chart here. It's annoying me. As you can tell. And they put the legend inside the chart. What is that? God, this is the worst thing I've ever seen in my life. I have a very good life, as you can tell. So, anyways, that's it for chapter whatever. Chapter 8. That's it for chapter 8. Thanks for coming by. Have a good day.